Good day to everyone. This is the assignment of EKC222 Chemical Engineering Thermodynamics. Our group would like to present the topic of heat capacity. First of all, this is the history of the development of heat capacity. Heat capacity was first discovered by Joseph Black, where he discovered two types of heat which are called sensible heat and latent heat. According to Pierre-Louis Dulong, he discovered the concept of specific heat capacity, where he defined specific heat capacity as heat required to raise the temperature of a unit mass of a substance by a unit temperature change. Next, according to Joseph Louis Gay-Lussac, the principle of additivity was introduced by him, where heat capacity of a compound could be calculated by summing heat capacity of its individual elements. In terms of development of modern concept of heat capacity, it was done by James Joule. Rudolf Clausius was the one who introduced the concept of heat capacity at constant volume and heat capacity at constant pressure. Lastly, Lord Kelvin, who established the Kelvin temperature scale that is directly related to the concept of heat capacity. At the end, heat capacity is defined as the amount of heat energy required to increase the temperature of a given substance by 1 Kelvin or 1 degree Celsius. For example, mercury in the thermometer applies the concept of heat capacity. Heat capacity is divided into two, which is molar heat capacity and specific heat capacity. Their difference is formula. Kindly pause the video to know further details. Heat capacity at constant volume, CV, is defined as the change in the internal energy with respect to temperature. All above is derivation of heat capacity at constant volume. Heat capacity at constant pressure, CP, is defined as the change in enthalpy with respect to temperature, and above shows derivation of enthalpy equations. The relationship between Cp and Cv for an ideal gas can be derived by using ideal gas equation and first law of thermodynamic equation. After derivation, we obtain the equation of Cp equals Cv plus R. Next is specific heat for ideal gas. For ideal gas, specific heat capacity is independent of temperature. Monoatomic, diatomic and polyatomic gas have different specific heat capacity. As for application of heat capacity, according to the definition heat capacity, it helps us to indicate how much heat is needed to heat or cool an object. When we relate this to the chemical engineering industry, this helps to provide details on the duration of heating or cooling process under a particular conditions and the resulting expenses of the process. Most importantly, it is one of the ways to save the production cost in the industries. In daily life, heat capacity is usually applicable in cookware design, where the body of the cookwares are usually made of stainless steel and the base made of copper. For your information, steels and copper or any other usual material to make cookware have low specific heat capacity. So, less heat is needed to raise the temperature of the cookware while cooking, and the food will be cooked in a short time. To find the heat capacities of a substance, we can obtain data from Appendix B, Table B.2. Then, calculate the answer via MATLAB or calculate manually. By using MATLAB, you also can get a plotted graph directly after the calculation. Let's take a look on the example question of heat capacity. Feel free to pause the video and read the question carefully. Right-hand side shows the movement of particles before and after compression. Firstly, we need to find the final volume and final temperature after CO. Both of the parameters can be calculated using PV/T, since the air is assumed as ideal gas. Temperature after cooling step is then substituted to find the heat released and the enthalpy change. Internal energy during cooling step with constant pressure is calculated through the equation of increment U equals increment HP increment V. During heating step at constant volume, heat absorbed is calculated through the equation of Q equals Cp increment T, and increment U is equal to heat absorbed. Overall process includes cooling and heating steps. Q and increment U can be calculated by summing up the heat and internal energy of the cooling and heating steps respectively. Lastly, work can be calculated based on first law of thermodynamics, where change in internal energy equals to heat absorbed or released plus work done. Here are some references used to complete this video. Here marks the end for our discussion today, and thank you for watching.